I'm working as a senior application engineer for the simulation. And this webinar is going to be about how we can step up your machine design quality using the 3D experience simulation. So I'm very excited to show you all the contents that we can bring into you for via 3D experience platform solution, which is a very powerful technique, powerful technology that Dassault system brings to the table. And let's start this journey together with this 3D experience platform simulation solutions. So just as an opening, I'm going to play in one. Let's see how the typical machine design challenges, machine design industry faces the challenges, how those challenges will be solved by the Express platform journey here. Let's go.
Manufacturing products and the massive urbanization of the planet, industrial equipment is in the core of our global transformation. To meet this demand, both products and manufacturing processes need robustness to minimize downtime and associated costs. Increased reliability leads to reduction in maintenance costs and significant savings for industrial equipment companies. Leveraging the equipment structural engineering industry process, industrial engineers design extended life while successfully meeting performance, operational, and manufacturing requirements. The equipment structural engineering industry process experience provides a set of solutions specifically conceived to maximize the life and performance of manufactured industrial equipment. Our solutions are powered by the 3DEXPERIENCE platform, a collaborative space where innovation is fostered through integrated processes from requirements to modeling to simulation. Years are fundamental components for all industries. Failure will often result in catastrophic failure of the entire system. Our efficient and accurate simulation-driven design process on the 3DEXPERIENCE platform helps ensure proper performance and predicts durability to minimize risk of failure and associated maintenance and downtime costs. Not only are individual components critical, but how they interface with each other plays a key role in their ability to perform throughout their lifespan. Our solutions allow you to efficiently assemble digital components and quickly determine the best design to meet durability and performance requirements. Processes themselves can introduce reliability issues. Welds are critical for the assembly of components and thus potential points of failure. With our structural simulation solutions, you can ensure that welding processes do not introduce undesired residual stresses that can cause failure in operation. Finally, complex manufacturing processes such as induction hardening can introduce defects in a manufactured product, such as distortions or cracks. These defects can be predicted and eliminated with a digital induction hardening process using our best-in-class technologies, ensuring reliability of products. With the equipment structural engineering industry process, you can ensure that your manufactured products will perform in demanding environments and stand the test of time.
All right. So I hope this gives a brief idea about what's this going to be about. So this technology, it's called 3DEXPERIENCE works, and the solutions that it brings together is a 3DEXPERIENCE platform simulation that we're going to see. So 3DEXPERIENCE platform is nothing but a platform where all the brands from the Dassault systems comes together and shares a collaborative dream, like give better solutions to a customer. So you can say we can have different areas that we work on targeted all the way in the same platform using the different brands from the Dassault system altogether. You can say there are different brands: SOLIDWORKS, CATIA, Simulia, and all other. So basically, we are going to work in collaboration with the Dassault system SOLIDWORKS and the Simulia brand altogether onto the 3DEXPERIENCE platform journey that we are about to see. So 3DEXPERIENCE platform simulation is nothing but your integrated simulation for your design. It is a design-centric and very comprehensive simulation with the advanced simulation capabilities there. It is a multi-physics simulation. We can of course couple the different physics domains together, and it is a on-cloud solution and scalable solution as per your industrial need. And of course, all the stakeholders can collaborate in between themselves with the help of this 3D experience platform simulation solutions. So that's the thing 3D experience works carries to you in terms of this. So just quickly have a look at an agenda. So for this presentation, the agenda will be as follows. As you can see, first we are going to see at how we can how we can work in this collaborative environment in the modeling and simulation environment that you can see. Then of course we'll also focus something on the strength validation, how we can do low and high frequency harmonic vibration analysis into the similar platform. And of course, let's say if there's any rapid motion in the machine, and how we can encounter those vibrations and how we can take care of those vibrations into this one. So that's how we are going to see rapid machine motion induced vibration, and that's to be taken care of. And finally, of course, we're going to focus on the advantages of 3D experience using this 3D experience platform. Of course, this will be told all together on the way journey, the advantages of the platform here. So let's focus on the first task here. So modeling and a simulation environment. So in here, of course, we are designing in the SolidWorks, and of course our data will be designing in the SolidWorks. And in order to make use of this cloud solution of 3D experience platform, we have to save our data on the cloud. So of course, we create a CAD, and with just a right click, we just save the data on the cloud. So that's how easy it is. So there's no import and export of CAD data. We're just saving a backup copy on the cloud, just like we do with the Google Photos. We just get these photos. We have one copy here on the desktop, or you can say on the mobile phones, and of course we get another copy on the cloud here, Google Cloud, just like that. So in here, next set of thing is, let's see how we can just a minute. Yeah, so we can have a quick and easy connection between SolidWorks and Similia through the SolidWorks connector. There's something called connector in between, and we can connect the SolidWorks to the you can say 3D experience platform. And through this connector, we are going to push our data to the 3D experience platform. So that's how easy it is. So let's have a look on the how we can do this on the SolidWorks. So this is our typical good old SolidWorks. We have my machine design ready, and through this one, I'll just right click on entity structure here, and I'm going to save my geometry on the cloud. And I have multiple options, and everything along with this revision and all, everything will be saved on this cloud solution here. So you can say once we save it, it will be going to save in the PLM environment, which is powered by the Innovia solutions from the Dassault system, and everything will be saved on the cloud, and a copy will be used afterwards for the simulation purposes there. So that's how we can easily pull the data here. We can see the conversion status at the right hand side, and once the assembly got converted, we are free to use this for the launching the Similia app. Of course, for launching the Similia app, you don't have to go very far. You can directly go it from the same 3D experience add-in here, and of course launch the 3D experience add-in here from this side. And of course, on the way, we can set up the simulation studies, we can set up the analysis title, types, and etc. directly from this environment here. So that's how your data is connected to the SolidWorks and the 3D experience platform side. Of course, I can go ahead and rename this simulation title and choose which type of analysis you want to select. And yes, with the help of OK, we can go to quickly go to the further studies to set up here. So in here, you can see we are actually not moving further away from the design. Everything is connected. Once you make a change inside the SolidWorks design, of course, this is obviously connected to the 3D experience platform. This change will be reflected there with the help of this update button. This change will be automatically being updated from the 3D experience on the 3D experience platform directly from the SolidWorks through the connector. So your data is, of course, will be every time will be in the sync, and every changes that you make will be reflected there. And if you want to store the revision, yes, revisions can also be stored there. So of course, next set of thing is of course we can how we can define the FEM, how we can define the materials, whether my materials will be carried here or what here, or how we can go ahead and define, let's say, finite element model, let's say, in order to make the analysis here. So of course, let's see how we can do is like automated finite element representation that we are used to do in the SOLIDWORKS simulation. Of course, this technology can be, of course, be elaborated to the 3DEXPERIENCE platform simulation as well. But the thing is, here we have very advanced meshing capability as well over the in the 3DEXPERIENCE platform. Of course, we can manage the part mesh in the large assemblies, configure the mesh using the mesh procedures. That is to say, of course, I can give a rule, and rule-based meshing can be done for all the parts all at once. So that's how powerful it is to do it. So let's have a look how we can do it. One by one. So of course, once I have brought in my design here, I can switch to something called model assembly design app, where of course I'm going to set up something called the FEM model. So FEM model is nothing but your attachment to the nothing but your finite element representation for entire your CAD model. And the finite element representation, based on the finite element method, we are going to solve this for the various problems for the structural analysis, vibration analysis, and all into it. And of course, I can make use of the different ideas here. For example, let's say if I want to apply meshing, of course, I can go ahead and do the conventional tetrahedral mesh that we are used to do into it. Of course, I can make changes to the any mesh here. Let's say you can see the to the right hand side. I can of course ignore some parts that I do not want to mesh. I can, of course, go ahead and assign different kinds of mesh to a different kinds of part. So here are, since this technology is powered by the abacus in the background, the meshing technologies from the abacus is being carried over here, and though these things can be, of course, be leveraged here in terms of the meshing as well as the solver capabilities in it. So here you can see once I'm done with the meshing here, I can of course go here and apply the mesh for the remaining parts. Here you can see remaining parts. I have just done it for the one sub-assembly here. Of course, I can go ahead and do it for the other sub-assemblies. And of course, if you want to do some other meshing, let's say rule-based mesh or that sort of thing, yes, you can of course go here and apply the procedures for the mesh. Currently, I'm just ignoring the parts which are not going to be meshed here and will be ignored in the analysis. So those things I'm taking care here. So once everything is set here, I can hit on OK, and of course, in the background, the meshing will be happening on the simulation here. So in here, yes, of course, we can define the materials. The materials can be defined in an easy fashion. Just like we go and apply the material in the SOLIDWORKS, those materials, of course, will be carried over here. Or with the help of material definition app, we can, of course, make and select and apply the materials to the parts, just as we used to do here. It's have a very built-in material database, and of course powerful search filters where it can zero down the materials which you want to do and apply the same material to the multiple parts using this section definitions. And that is section definitions come very handy whenever we are applying the same section properties to the different parts. So that's how we can do it here. So in here you can say once we go and assign a section to the, let's say, different parts, I can assign the name of the section. I can select which things I want to carry here, and of course assign the material and behavior for it, let's say with the plasticity and all. We can of course select all the assembly at once, or of course we can ignore some of the parts here, let's say if you don't want to do. And of course with the help of this material palettes and the search filters, I can go here and choose from the extensive database which material that you want to apply. So let's say if I want to apply the plain carbon steel, I can go ahead and here choose which simulation properties that's taken care of, whether you want to solve it with plasticity or without plasticity model. And those things can be taken care in the background with the help of this model definition app. Of course, this procedure is to be repeated for the different parts, or the section definitions to be repeated for the remaining parts that you want to take into the analysis. And of course, every part should have a section and the material definition assigned to it in order to solve this in the finite element model. So yes, of course, we're going to assign a solid section. We're going to apply the drawing material here. Of course, it's not only just limited to metals, the plastics materials and all also be taken care here along with that. As you can see, copolymer materials will be assigned to these parts here. I think these are the caps here. And in the same way, of course, we can assign the rest of the parts and materials with that. So with this material definition done, let's move on to the further step in the analysis. And every step is, of course, guided here by something called the assistant panel. So you have your assistant panel ready, and it will guide you through all the step procedures that you want to follow. And of course, let's say if I want to do the tie and coupling, and if I want to do and define the assembly interactions such as the ties and couplings and connectors, how those are coming together, how the components are coming together. I just want to do it in the simulation definition. So this is where we can make use of this thing. Let's say you can set assembly interaction into it one. Of course, the ties, it's nothing but it will bond all the part together so that it will behave as a welded part or a single part here. Coupling will track the key results at the tooltip, because here, and since this is a water jet machine, and here I just want to just want to see how much this let's say self weight and all will affect this thing, affect the accuracy here. I just want to track the results at the tooltip. So it will work like tracking my results data there, tracker for my results data there. Connectors will of course control the relative motion between the parts. So that's how the connectors or couplings will take care here. So here, in order to assign that one, of course, just I want to go to the connections, and here we have something called tie connection. Of course, with the help of automatic tie detection, we can go ahead and we can select for the whole model, and it will automatically detect which components are touching and which components will come into the connections. And of course, it will pinpoint which components are touching, and it will suggest you these components can be assigned with the tie connections. And there we can take a decisions where we want to assign the tie connection for. So of course we can select the portions that you can see. Once we hit OK, everything will be tied together just at the bonded contact in the SOLIDWORKS. So once we assign this one, we can go here and of course represent the engineering connections and rename this with the tie connections that we want to see. So likewise, let's say if you want to create a link connector, link connectors can be of course selected here. Links between the two, you can say the supports or the parts can be created. Along with that, we can assign the translation and rotations definitions for this link connection. And here you can see this is sort of a ball joint that you know. This is a link between the two ball joints, and this is how this small degree of freedom will be taken care for. And here, of course, once we select that one with the help of this link connector, you do not have to take this part into the account, since we have ignored this in the meshing. And just want to save the mesh calculations, we do not want to we do not want to include that part, but we want to take the effect of that part into the account. So that's where the connection is being taken care of. The between parts you can see here is taken care with the help of rigid body elements, and with the help of this coupling we are depicting the effect of that rod into the simulation without taking the CAD model. And finally here with the help of coupling connections, of course we can track the tooltip. With the help of this thing we can assign and track the results data all across that tooltip here. And you can see that towards the left hand side, everything that we do has been recorded onto the feature manager tree here, and along with the definition, along with the CAD, the simulation and all of the stuff will be recorded to the left hand side. And at any point of time, if you want to change things, You can just have to go to the left hand side, edit those things as you feel. So defining and editing is, of course, is a single way task here. So that's how we can have a seamless CAD and CA associativity, and of course, with the help of very quick and few steps, we can of course define the simulation setup along the way. So now we have defined the modeling and simulation environment. Now let's have a look at how we can do the strength validation here. For the strength validation, we just have to go for physics scenarios, and we have to create one scenario here. And of course, we can set up a scenario likewise. So let's consider a scenario first here. So my scenario here is I have to analyze the structural weight, and of course I want to see the tooltip reaction from the water jet is how this thing is affecting my structure here. So since this is a water jet machine, from the nozzle tip to the workpiece, there will be a water connecting to it, and this is let's say if I assume that the water is incompressible fluid and there's no way to escape it, there will be a reaction to it, and this is going to be giving the reverse back reaction to the tooltip, and from that reaction every structure is getting affected. So I just want to analyze this scenario from here. So the loads I considered here is nothing but a gravity, tooltip force, which is you can see the backward force here, how this tooltip is going to apply a fluid pressure load onto this one, and finally the clamp. So this thing will be fixed at the clamp location whenever we are machining here. Of course, this head will be moving during the machining, but let's say if I consider a static scenario right now, and just to test this assembly from the static standpoint, and in that case I just want to assume these things are locked together and everything is bonded together, and then the force will be coming. We can see it as a starting moment of this water jet machine. So here, in order to just do the scenarios, what I can do is I can go to mechanical scenario creation app. Of course, I can go here and create the static step. Static step is this is a non-linear step, and of course I can define a time increment, and that's how the simulation becomes very accurate, since we are using the non-linear analysis from the start. So in here I can go and select which areas that I want to clamp together. Clamp is nothing but those are the coupling, so those are the you can say that those 4 bolted portions there. I can assign the gravity to all the models. Of course, this arrow will indicate that the gravity load is assigned, and finally we're going to assign the tooltip force at tooltip force here. So in here I can go here and select the connections. Since we have assigned the coupling there, I can directly assign load to the coupling, and coupling will transfer that load to the tooltip here. So that's how this thing goes on. Instead of selecting the part, you can say all the geometrical nodes will be concentrated to the coupling, and then from this coupling this load will be transferred to those all geometrical nodes, and then the rest of the geometry is here. And of course I can of course apply the translation here in order to get this effect into the account. Let's say get the effect into the account. Let's say servo motor lock here. So in here I am assigning the 0 translation, that is there's no relative motion between the parts along the way, and that's how we are going to test it for the self weight and the gravity tooltip force. And of course I can perform quick model and scenario checks. So this is a very important step here, because whatever I set up, I want to make sure that whether I set up it correctly or not. That's how the model and scenario check will help you out. It will tell you whether is there any problem with your setup. You need to have extra information. If you are needed extra information in the diagnostic viewer, we can of course go ahead and view what information needs to be fed to the solver. And this is how the simulation are made error free for the setup standpoint. All right, so everything is set up now. I just want to run the simulation. So there are a few advanced options available here. So in here you have something called running simulation on the cloud, and this is very fast, let me tell you. So of course, we can make use of the high performance computing resources along the way. Of course, it will reduce your software and hardware cost along the way, and of course, it will maintain your data consistency, and of course, it will streamline the processes along the way, and it will improve the collaborations. Improve the collaboration, that is to say, let's say if your colleague or your managers want to see what's going on during the design or in between the simulation and all, you can of course just share that simulation link there, and of course he can also view on the cloud along the way. So that's how everything will be taken care along the way. So once everything is set up, I can of course go here, hit on the run simulation button, and of course we have options for the cloud computing and the local computing as well. I can select how many number of cores that you want to utilize. You can see these are local interactive is your local computing options. It will utilize the local cores. Let's say if you are using 6-core machines, it will utilize 6-core up to let's say 8 cores it can utilize here on the locally. But on the cloud, you can go here up to 144 cores. Superb, isn't it? So with the help of that, we can select how many number of cores you want to utilize. That's how the solving time will be reduced down. The number crunching will happen on the cloud, and you're free to do another work in the meanwhile. So that's how the productivity can also be increased during the simulation setup. And of course, we can monitor the progress. We can view the plot. We can of course access the diagnostic data. What's going on in the solver background? What are the iterations? Whether my plots are converging or not, or how my convergence criteria has been kept. Those things can be plotted all together with the help of this simulation status window. So likewise, yes, you can see the iterations here. The iterations will continue to do it, do its job. It will do the number crunching, and of course, finally, at the end of it, the simulation will extract the results and save the simulation here on the cloud. So everything will be done very smoothly here and very fast with the help of this cloud computing options. And finally, of course, we can hit on the results button. The results will be shown here likewise. So let's have a look what we can do in the physics results review here. Of course, my objective was to analyze the structural effect of structural self weight and the tooltip reaction from the watershed. And we are going to evaluate this from the standpoint of von Mises criteria, because there are more ductile materials involved into this one. Is the structure stiff enough to resist these structural loads? That's my primary objective. And I just want to see how much displacement will it cause, because this displacement is ultimately is going to affect my accuracy of cutting in its place. So that's how we can see with the help of displacement plot. And of course, I can check the coupling responses. Shows the concentrated loads and displacement and the tooltips. So since this tooltip is a very essential part in the cutting process, I just want to track the niche and detailed results around this one. So this is how we can do this with the help of the displacement by tracking the displacement and the tooltip. So of course, once we hit on the results button, we can of course see these results in the fashion of the animation, in the fashion of the structural plots here. Of course, we can track down the von Mises stresses. We can of course track down the results that has been raised here, and you can see the displacement results along the way. And it's very intuitive to do it, just like we do in our regular SOLIDWORKS environment. So likewise, the listings will be tracked down for the every step of the analysis, and of course, last step will give you the final results here. And of course, with the help of animation, we can see how the response of the structure is going to be for that applied load conditions. And of course, once we apply the load there, definitely in the same fashion, we can do it in the physical environment here. And the probe displacement results will guide you about how we can probe the displacement along this tooltip. So here I'm selecting multiple points along this tooltip, and when I go to the XY plot, I can select the which variable I want to track. Here I just want to track the translation. Of course, I'm interested in magnitude only. So once I hit OK, it will tag the tooltip reaction or tooltip displacement results on the way. I can pin it down to the left hand side, and of course I jot it down to the how this tooltip is going to behave under this loading condition once the jet is starting. So that's how we can track down and interact with the XY plot here. The detailed investigation of the results frame by frames can be done with the help of this XY plot, just as we do. Yeah. So in here, finally, let's move on. This concludes the structural strength validation, which ensures the structure has stiff responses to the static load conditions. But of course, this is a machine, and there will not be ideal static condition every time. There will be motion, and due to this motion, there will be some vibrations, and this vibration will also affect the frequency. This will also affect the accuracy of the machine here. So that's we want to take care of. So here we have a powerful low and high frequency harmonic vibration study that will tell you about how we can of course track down the effect of the vibration on the machine, how the accuracy is getting affected during by when we subject this machine to the vibration. And of course, if we take appropriate measure using this data, of course we can reduce down the effect of the vibration that is coming onto the machine. So that's how we can do it here. So let's see how this thing will be processed. So in order to do this thing, I'm just going to extract out the resonant frequencies first. So in here, we can see, in order to understand this resonant frequency, when the frequency of the excitation load coincide with the natural frequency of the structure, the structure resonates and it amplifies the loads and amplifies the displacement that leads to be catastrophic failure. So you can see towards the right hand side, there's one video that has been playing. It will tell you, let's say this is a plate, and where where you can see there are tiny particles that have been spread out, and of course you can see what happens at a different frequencies, how this particles are reorienting itself with the help of this vibrating frequencies. So this is not a magic, or this is not a magnetically placed there. Of course, with the help of the frequency that is in subjected to, you can see I'm changing the frequency values here towards the left bottom side. So you can see with the help of this different frequency values, it is showing you different shapes. Please remember this, it is showing you the different shapes, and that's how we can, in the frequency analysis, we call it as a mode shapes. So likewise, we can do further things here. So in here, we are going to define the frequency step. We are going to define, we are going to extract out the frequency for the free system with the no loads. We are going to extract out its natural frequencies, understand the mode shapes and the load participation factor, change the geometrical conditions like geometry, boundary conditions, material stiffness. We are adding the dampers, and we're going to change the vibration characteristics along the way. All right. So in our machine, let's correlate this application with our machine. In our machine, my main source of vibration here is pump pulsating water jet. You can see for the low frequency vibration, a pump is a low frequency vibration source. A water jet is a high frequency vibration source. Here you can see it is rotating at 500 rpm to the 1500 rpm. Let's say if I convert that to hertz, it's like 8.33 to 445 hertz around. And the base excitation here is around 0.01 millimeters. And excitation load is around 20 pounds. We can say we can convert this as 1500 hertz. And the damping we have to consider, because there will be a structural damping inside it, and or let's say if I put a vibration pad there or rubber pads there, there will be some damping will be there inside the system. We can of course consider that as a damping ratio along the way. So in order to create that one, what we can do is we can create the new analysis case in the same analysis case that we have studied earlier. So you do not have to define a study, it will be all tracked down here. You just have to define a new step. All the associated finite element that we have created earlier will be tracked down in this study as well. So you do not have to go further and change the finite element every time. So of course, we can go ahead and define a frequency step. We can define which frequencies up to which we can want to study. Initially, we are going to study for the 1500 Hertz. We are going to define two studies here, by the way. Here, of course, I just want to change some restraints for this one. And of course, I'm going to select the clamp forces once again. And I'm going to assign the fixed displacement constraints for some translation here. Let's say for the servo motor lock here. So just in the Z direction, it is going to be a frozen one. It's not going to move there. And in the, of course, this another servo motor is going to be not going to move the say X direction. So in here, I'm just going to create an harmonic step, and this is going to give us about the central frequencies that we want to extract. So from let's say lower frequency from 1 Hertz to the upper frequency of 500 Hertz, I can extract out the natural frequencies there. And of course, we can, if you want to define the frequency and damping factor as per the frequencies, in that case, we can enter the damping ratio, or you can say the damping percentage. Currently, I'm entering the 5% damping. And finally, here we're going to provide an external base excitation to it. And we are going to provide this in the amplitude form. And there's no sudden excitation here. Smoothly, this is going to be exciting, or you can say the force is going to apply. That's how uniform base excitations will be provided to the assembly here. So displacement based motion, we can of course select out to apply the loads, and they say from the pump. And of course, we can review this multi-step analysis. Here, we are going to first do the frequency step, then we are providing the vibration analysis step. And this is a multi-step analysis. And of course, we want to extract out the key results with the help of output request. We can select which results you want to extract out. Here, we are interested in the stress and the displacement primarily at the tooltip as well as the globally as well. So I'm selecting the tooltip here, selecting the coupling for the tooltip, because the coupling is combining all the nodes together from that phases. And for the tooltip, I'm just extracting out in a very detailed fashion, because this is a very important part in this analysis. So likewise, the setup will be created. So let's set up another study for the high frequency. Since we have set up this study for the low frequency, now let's set up the same study for the high frequency. In the similar fashion, the associated finite element will be linked to the same this one. And of course, we are going to go ahead and create the frequency study once more. Here, we are going to set the higher frequency range. And of course, with the help of that, we see in the similar fashion, we're going to set up this entire study altogether for the high frequency applications here. So once we set everything up, we are going to, of course, run for once again for the model and scenario check, whether to see whether my setup is correct or not, and then we're going to run it. And once the setup is run, let's see how we can see the physics results. So our key KPIs here to how to identify the key resonant modes, displacement and the tooltip. And my criteria is it should be very less than you can say 0.006 inches. And of course, we're going to compare the results of the low and high frequency vibrations in here. So displacement plot shows how is there any excessive displacement or deformations in the critical areas? And of course, coupling responses shows the displacement and acceleration on the tooltip. And of course, by side-by-side comparison of the results from the low and high frequency side, we can make use of this compare result tool and extract out the meaningful outputs out of it. So here you can see the low frequency results will tell you the mode shapes. So the structure is going to reorient itself as per this mode shapes. And when this mode shape and the frequency combine with your external excitations, that's where the resonance occurs. And we are going to check the resonating conditions here also with the help of that. So let's say if I go for the low frequency applications, so you can see low frequency applications have the displacement values. Here you can see at the different values for the different displacement tooltips. Different frequencies here. And let's say if I see the results at the tooltip for the low and high frequency applications because of this pump vibration response. So you can see we can compare the different results here altogether. So there are 3 data points that we want to track. So how these are going to affect during this vibration frequencies. And here you can see the peaks where the resonance conditions have occurred, but those displacement in inches are quite high compared to that one. So of course we can track out the pump responses. The displacement tooltip responses for the pump vibration source. Here we are tracking it for the higher frequencies than 500 hertz. From 0 to 500 hertz. So here you can see how this accelerations and the displacements are being tracked down here with the help of this frequency step. So now the high frequency results here, of course, we can view the different mode shape for the different frequency values, and the similar plots can be tracked down for this one for the high frequency harmonics. So here, of course, we can view the deformation around the resonating frequencies, review the tooltip displacement and acceleration responses with the help of this high frequency analysis report. And finally, when everything is done, we are going to compare the results from the lower frequency and the higher frequency altogether. So that's give us an idea about how the structure is responding to the lower and the higher frequencies in that way. So here, right now I'm comparing about the displacement at this highest resonating frequency peak, which is around the 1000 hertz. So that's where the problem is going to occur, and we are going to express out the maximum displacement. And finally, with the help of this compare results, we can go to display and compare results. We can select which results we want to compare, and it will of course tell out the different it will combine the results from the different studies, and of course everything will be same shown in the same window. So that's where we can see for the lower frequencies and the higher frequency how the results are higher here, and whether it is area of my concern or not. And my criteria was it should not be greater than 0.006, but here you can see it is still lower than that value. So that means my machine is pretty much safe, and okay, whatever design I have done is pretty good from that standpoint. So that's how we can evaluate and ensure the minimal vibrations at the tooltip with the help of this low and high frequency vibration analysis. So this is for the basic vibration analysis. Let's say if I want to consider, because this is a cutting action is going to be there, and this cutting action is performed based on the servo motors, and it is going to drive that tooltip in the profile cutting. And I'm just want to evaluate what happen. Let's say if there's any rapid machine motion induced vibration, I want to make ensure that my accuracy will be very high in that case. So here I'm just going to focus on the rapid machine motion induced vibration, and for that we are going to set up a physics scenario where I'm just going to use the fast machine motion test, where the tooltip in a circular motions will be depicted. Rapid movement of a bridge in XZ direction, XZ direction, For this, we are going to duplicate the finite element, reuse the existing mesh and add rigid bodies to it. So you can see this is a rigid body and this is one is the flexible body for me. Rigid bodies, of course, I mean, neglect the deformations, but the flexible body allows the deformation there. And we are going to see it with the help of this implicit dynamic technique there, which works based on the minimal energy dissipation, and it will help to resolve the vibrational responses. And of course, we apply translation to in the periodic fashion, x direction cosine, z direction sine fashion. So that's how we're going to evaluate this scenario here. So in order to set up that study for the rapid machine motion induced vibration, we are just going to duplicate the finite element representation. We just want to keep it separate for this one because we are converting some bodies as a rigid body and some bodies as a flexible body. That's why we are duplicating it. And of course, we are going to assign a duplication prefix. Here, once we hit OK, we can go ahead and convert out the frequency. So now I have converted and assigned the different finite element model here, and just want to select that for definition of the structure here. I'm just you can see since we have duplicated it, all the nodes and material properties and the section properties will be copied here, but a different finite element model has been created altogether. So now we are going to create the new analysis case and we're going to assign that finite element model to it. Sorry. So in here, we're going to set out the new name for this analysis case, like machine motion vibration. And we're going to study the response from the rapid machine motion. We're also going to select out the second finite element model, which we have just attached a prefix to. And of course, it will duplicate everything together and attach that finite element model to our new analysis case. I do not want to consider the other assemblies as a rigid assembly. So here I just want to create and select out those bodies which I want to consider a rigid body. So in here, I'm just assigning this middle tube and all those components except this one as a rigid components. The rest of the guys will be the flexible parts to be considered. So just have to make a selective. You just have to be selective about which parts you want to consider as a rigid parts. And that's all to it. And of course, we're going to fix one point for the rigid here. In here, another thing is rigid bodies have negligible deformation. It will help us to have the faster solution time, because actually we are ignoring the effect of this rapid machine motion onto this rigid body, and so solver is intelligent enough to ignore the effect of this machine motion onto those parts. But yes, the area of concern here is the tool tip and that the tool heads and all. So that part will be selecting as a flexible part, and there the very detailed and niche calculations will be done, because that is a very sensitive area and that's going to affect everything along the way. So in here, just as this go on, the rigid bodies will be selected all out here along the way. And finally, here we can see we can select out the, of course, sorry, yeah, just let me just go back. We just select out the rigid bodies group here, and similarly we are going to select out the flexible bodies also towards this one. So this is going to be one by one. So we can make use of a connection manager in order to depict the connections here. So here you can see once we have defined the connector along the way, and we are going to make use of this connection manager in order to assign the flexible motion to this component, in order to introduce that motion effect into the account. So of course we can turn off the connection at the local subassembly level, so that we can make use of this connection manager. So likewise, this local translation connectors have been turned off. So now we can go ahead further in order to make use of this connection manager to turn on the connections at the main assemblies, so that there will at the subassembly level there should not be any movement, but at the main assembly level there should be a movement. So that's how we are going to depict the motion into it. And for that we are going to select, we are going to drive this motion with the help of the support vortexes. So here we are going to assign the translation connector to those vortices, and we're going to take control of the motion based on this this connector or vortices here. It describes the predescribes the translation in only in one direction between the connected points. That's how the connection is useful here in order to depict the motion. So likewise, you can see the connections is been described right now with the help of this one. And now in the next stage, we're going to remesh this assembly, or you can say we are going to update this assembly and assign the implicit dynamic step. And this is going to be another implicit dynamic step, and we're going to see the application. We can select the applications. Of course, we're going to fix some displacement for the left and right rigid groups. We're going to freeze out all the translation as well as the rotations. We're going to select out the finite element, that's area of concern for me. And of course, I'm going to assign this fixed displacement to the other finite element representation like billiard tube and all, where I'm only going to fix out the rotations here. So once this thing has been done, I'm going to assign the setup for you can say the tabular amplitude, where the smooth motion is be there. Of course, whenever we are trying to cut the portions together, we assign the smooth motion to the tooltip, and this smooth motion, there will not be any jerky motion. Since I want to use such a kind of motion, I'm going to assign this tabular amplitude there. Of course, we can apply the loads, create the Z direction connection translation. Here I'm just going to select out the link connectors here, dynamic translator altogether, and activate the translation in that direction. And with the help of this dialog box and the previous dialog box for the amplitude combined together, and the magnitude and the smoothness of the motion will be taken care along the way. Right. So here we are also going to study the effect of the gravity, and of course we are going to track out the output request for this one. Output request is nothing but which plot you want to extract out from this one. I'm going to select out translation and rotation, all translation and rotation as an history output for the tooltip. History output will give you very you can say the zoom in result for that a particular area. So in here, once everything is done, you can of course review this onto the left hand side. Everything will be stored there, and of course we're just going to run out the final study that you want to see. Here I'm just going to make use of the cloud computing HPC environment, and of course it will consume out almost 91 tokens here, and 36 cores will be utilized, and it will be very fast running study here along the way. So like how we can set up the study, now let's see the results here. We can analyze the assembly displacement during the motion. We can review the key responses at a tooltip, and we can evaluate is the maximum stress in linear range during the motion. If it is in a non-linear range, of course there will be a permanent deformation, and that's the area of concern for me. And of course I can neglect that thing along the way. So of course, von Mises stress plot answers this question: are the dynamic stresses are in the linear range or not? And of course, displacement plot shows if there is any excessive deformation in the critical areas. And the coupling response shows the tooltip path, displacement, and acceleration and the tooltip. So here, let's see how we can do it down. So once we play the simulation, we have depicted the motion such as the tooltip will be moving in the similar fashion. So that's the motion we have depicted here with the help of tabular amplitude and the coupling motion that we have assigned. And of course, we can review the stresses, displacement likewise. The tooltip, of course, displaces as we expected. And of course, we have expected the assembly and behave in that way when we define the tabular amplitude, and that's how it is going to be doing here. So now, of course, I can go ahead here and see the critical results with the help of plots and the sensors. So let's say if I click on the XY plot, I can filter out which area I want to select. Let's say first of all, I just want to see the displacement and the tooltip. I just select the variable there. I can of course support for the tooltip is nothing but your coupling, and this is how the tooltip is going to be in the motion. We have assigned that particular motion to it, and of course it is giving you the x displacement in the same fashion. Y displacement, let's say if you track down, you can compare the different displacement values. So cosine and sine functions was assigned beforehand. So here we are tracking the same amount of displacement. And same for the circular tool path, we're going to assign and the tooltip responses, and we're going to track down these responses together. How, let's say for the circular path, whether is there any deviation from the structural response and the machining state. So we are going to verify the sine and cosine profile, input profile created for circular tooltip path. And is there any deviation or is there any maximum displacement changes, or I can say the deviation from this thing. So that's what give us an idea whether is there any additional displacement caused by this rapid machine motion induced vibration that is affecting my accuracy here. So that's how we're going to plot out everything together with the help of the superimpose XY plot, which will verify the sine and cosine profile created for a circular tooltip path. So here, yeah, first we can jot down these results for different profile paths, and of course with the help of animation we can give the idea about how this thing is behaving. And of course there are a few legends toward the right hand side where we can review out the maximum displacement differences in between that one. So likewise, same thing goes for history plots as well. History plots give us an insight about how the acceleration response is there for this one, and this is very critical to track down because if there's any acceleration, or I can say the change in acceleration, there will be a jerk. So here, let's say when the change in acceleration with the help of with respect to time, there will be a jerk. You can see in the initial stage time, let's say 0.2 second or 0.1 second previous, there will be a slight jerk here, and of course that can affect the initial level accuracy for the tooltip. But the area of concern is for that area, how much is the tooltip getting displaced in the inches. So yeah, in the initial stages, tooltip might have some problem. So while starting the machine, we have to start very at the remote location, and then bring that tooltip to the profile cutting location. That's how we can of course improve out our accuracy with the help of this one. So that's a clear indication here. And at the starting point, because there's a jerk, there will be some effect in the accuracy, let's say around from the starting point of let's say 0.1 seconds or 0.2 seconds. Then everything will be stable, and that's how the accuracy goes continues in this one. So of course factors are considered here where the vibration noise and the servo drives for the manufacturing precisions, and effect of that will be considered here in the rapid machine motion index vibration, and how we can improve out those areas also it's been taken care of. So yeah, last thing here, nothing but the advantages of platform. It can help you to collaborate and communicate anytime, anywhere, on any device. So it's a beauty, isn't it? So in here, of course, we can co-design, co-simulate, and collaborate all together onto this power of 3DEXPERIENCE platform. So here you can see I have created my personalized dashboard for the application with the help of the 3D Play app. I can, of course, my colleagues also can, of course, participate, and my manager also can give me reviews about tooltip displacements and all. With the help of this community, I can, of course, share my things on that community. This is like your personalized social media for your industry only, and only your industrial personnel will be seeing this thing on that community. And of course, I can yeah, here to the left hand side you can see there's a 3D map, and the communities, whoever here entered anything here will be recorded in the, just like we do it on the social medias. And of course, I can enter out and link any suggestions that I want to give here. Yeah, so I can type in the comments, I can like the projects, I can create an idea. 3D space here where, and the collaborative space where all the data is shared on the cloud storage. If I want to drag and drop anything on for the review, I can just go to the collaborative space, drag and drop it here into the simulation review window. With the help of this physics simulation review, I can, of course, review the simulation without opening the simulation app. This is just a player, you can say, for the simulation here, and of course I can do it very nichely without the simulation app here. So of course I can play the animation, I can track down the probe results, I can take the section views, I can, of course, share this on the community for the further reviews for the other guys. Yeah, likewise it will go on and on. So here, of course, I can make out the few comments, chosen comments, like maximum displacement is below 0.0002 inches. The acceleration response looks good, and this design is acceptable for the further process. And that's how the community, in between community conversations can happen. So likewise, we can go further on. There are a few tools for the project management as well, where we can track down the projects just like we used to do on the Excel. But yeah, this is very intuitive, where we can track down the responses from all the other guys who are collaborating on the same platform, and we can track down the projects very neatly. So the 3DEXPERIENCE platform gives an advantage where we can collaborate, communicate anywhere, anytime, on any device. So that's how powerful technology 3DEXPERIENCE platform brings you to you. And in the summary, you can say this is the best tool for your simulation solutions. So the key takeaways is we can, of course, create a simulation-driven design, accelerate innovation, leverage cloud computing, improve the quality, and finally ensures the functional efficiency for your design. So 3DEXPERIENCE Works is a integrated, design-centric, comprehensive, multi-physics, on-cloud scalable solution where you can collaborate with everyone within your organization. So that's all to it. Thank you so much. If you have any questions onto this one, feel free